Hey man.
Oh, hey, what's up?
Not much. Hey, playing solitaire.
Yeah, it's so much fun.
Sweet. Hey, did you know we have a math test tomorrow?
Wait, what? We have a math test?
Yeah. Related rates.
Oh crap, what are those?
I don't know either, man. Maybe we should check a video online.
Alright, let's do it. You two probably have it, right?
Yeah.
Oh, sweet. We found one.
Hello everybody, I am Professor Fisher, and today's YouTube lesson will be over related rates. Now, as you all know, calculus is extremely useful, and one of these many uses is in solving problems where the rate at which one quantity is changing is related to the rate at which another quantity is changing, hence the name related rates. So in order to solve these types of problems, we'll need to use something called implicit differentiation. What you do is you start by writing an equation that relates the variables which you want to examine. So we'll start with an equation that we all know very well as an example of this, and use the Pythagorean theorem. A squared plus b squared equals c squared. Now, in order to use implicit differentiation, what we do is we will differentiate both sides with respect to time and using the chain rule. So we'll start with the a squared term, and we all know well the a squared, or the derivative of a squared is 2a, and then the derivative of a with respect to time will be dA dt. In order to finish this off, we have 2b dB dt equals 2c dc dt. Now, in my many years of teaching related rates, I have found that the best way to get students to learn is by doing examples. So we will do one of those now. So for our first example, let's say there are two cars sitting in an intersection. At time t equals 0, the first car leaves the intersection traveling at 3 meters per second. Let's say 1 second later, or t equals 1, the second car leaves the intersection traveling north at 4 meters per second. So let's define the distance that this car has traveled east as a, which means the rate it is traveling is dA dt, or in this case we know is 3 meters per second. Similarly, we'll define the same for the car traveling north. We will say that the distance it has traveled is b, and the rate is dp dB dt, which we know is 4 meters per second. Now, there's also a third distance in a rate which we want to examine, which will be the distance between the two cars, which we will define as c, and the rate at which they are traveling apart from each other as dc dt. So for this example, let's try to find the rate at which the two cars are traveling apart from each other at time t equals 2, or 2 seconds after this car has left the intersection. Which means that what we're trying to find is dc dt. So let's draw another picture. Here's the intersection. So after two seconds, we know the car traveling at 3 meters per second will have traveled 6 meters, and is still moving at 3 meters per second. Now recall that the second car left the intersection a second after the first car, which means it has only been traveling for 1 second at 4 meters per second, which means it has traveled 4 meters. And is still going at 4 meters per second. What we also want to find is the distance between the two cars, which we define as c. As you can see, we have a right triangle with sides 4 meters and 6 meters, so we can find this third side using the Pythagorean theorem. So it's going to be the square root of 4 squared plus 6 squared, which is equal to the square root of 52, which is equal to 2 root 13. So now let us go back to the equation that we used earlier, and we're going to plug in the values that we know and then solve for dc dt. So I'll go ahead and fill those in. We have 2 times a, which we found is 6 meters, times dA dt is 3 meters per second. We're going to go ahead and add 2 times b, which is the distance the car has traveled north, is 4 meters, times dB dt, which is 4 meters per second. That is equal to 2 times c, which we found down here is 2 root 13. times dc dt. So you can see from this point forward it's just algebra, so I'll go ahead and do that and solve for dc dt. So over here, 17 over square root of 13, or if you'd like to rationalize it, 17 root 13 over 13. So for our second example, I'm going to set it up for you, and then I'll let you solve it and see if you can come up with the right answer. A cone with a diameter of 20 centimeters and a height of 20 centimeters is being filled with water at a rate of 10 centimeters per second. How fast is the radius increasing when the volume is 262 centimeters cubed?
Okay, so first we have to find R in terms of h, right?
Right. But this cone is like a similar triangle, right?
Mm-hmm.
We have a height of 20 centimeters and a diameter of 20 centimeters. That means our radius is 10 centimeters. So our height is equal to 2r, always. So if we use our volume equation, volume equals 1/3 pi r squared height. Volume actually equals 1/3 pi r squared times 2r.
Which equals 2/3 pi r cubed.
Right.
Okay.
So we have to find the rate at which the radius is increasing when the volume is 262 centimeters cubed, so we need to solve for the radius. So 262 equals 2/3 pi r cubed, and if we use the TI-89, the radius is 5.
Okay, sweet. That's convenient.
Nice. So then we can go back to our volume equation. V equals 2/3 pi r cubed, and differentiate using implicit differentiation. dv dt equals 2 pi r squared dr dt. And we want to solve for dr dt. So,
And we already know what that is.
Right,
dv dt is.
yeah, that's 10.
So 10 equals 2 pi r squared times dr dt. And r equals 5, so
2 pi times 5 squared dr dt. So
dr dt equals
50 pi r dt. dr dt equals 1/5, 1/5 pi.
And you should be getting the answer as dr dt, or the rate at which the radius is increasing, is 1/5 pi centimeters per second.
So, how fast is the surface area of a sphere increasing when its volume is increasing by 10 centimeters cubed per second and its radius is 8 centimeters?
dv over dt equals 10 centimeters cubed over seconds, and r equals 8 centimeters. So by differentiating the equation for volume of a sphere, dv over dt equals 4 pi r squared dr dt.
Then, that means 10 equals 4 pi times 8 squared dr dt, so dr over dt equals 10 over 256 pi.
Now I can use this with the differentiated surface area equation to determine the change in surface area, so ds over dt equals 8 pi times 8 times 10 over 256 pi, which equals 2.5.
Hey, Dr. Delaney, are we going to get our quizzes back today?
Yes, you will. In fact, you both did extremely well.
Sweet, we got A's! Nice. Yeah!